Today we learn about digital code. Okay, digital is a string of many digits to represent number or characters or action or condition or anything. By representing various things with different code. For example, if we have 3 bits of binary code, it can represent by using 00 or 001 or 010 until 111. That means it can represent up to 8 various things. Okay. So for n bit binary code, it can represent up to the power of n. Okay. The binary string that used to represent something is called code word. But the string that not used to represent that not used to represent anything or no meaning is called non-code word. Okay, let's see the first one. Character code. For example, in English. In English, there are how many alphabet? 26, right? A to Z, right? Okay. Lowercase and capital. Okay. That means totally there are 52, right? And some symbol. For example, question mark, full stop, colon, semicolon, and so on. Totally, maybe it's greater than, not sure, 70 or 80, right? So, how many bits need to represent this kind of letter or symbol? 6 bits? Enough or not? No, because 6 bits maybe 2 to the power of 6 is 64, right? So it's not enough. Okay, maybe at least 7 bits. Okay, the standard code, okay, to represent this kind of character, okay, is called ASCII. ASCII code is from American Standard Code for information interchange. For example, this table. This one is B6, B5, B4, B3, B2, B1, and B0. For example, if I want to represent D, okay, we use what? Use 100 and 0100 for this capital D. Okay, letter D. Okay, D is 100 0100. I is 110 and 1001. G is 1 and I again, and T A L. Okay, to represent this word digital or this hey. Okay, this one do HEY and this mark. Okay, so this is for ASCII code. Okay, the next consider this one, this plate. Okay, this plate. Okay, for example, if let's consider this plate. If the plate connect to something like a motor, okay, when you rotate this plate, and that I setting some sensor like this. If I paint some color, okay, blue or black or some dark color, okay, and that I set some light source like LED, okay, to emit some light to this plate, and you have some sensor at here, light sensor. I mean when the light, okay, hit this plate and some reflect light back to this sensor, and let sensor detect and give logic 1 output. Okay, if this plate rotate and some transparent area, okay, come to this position, that means the light may be passed through this transparent area. So few of light reflect and going to the light sensor. So the output of the sensor now may be 0. Okay, based on this setting, what happens if this plate stays still? Okay, don't move. So it doesn't move. That means the output from the sensor may be constant one. Anyway, if this plate rotate, so what happened? The output should change to what? To 1 0 1 0, right? Okay. Anyway, what happened if this plate turn into this counterclockwise direction? How about the output? The output also change between 0 and 1, right? So you cannot see the difference between the output of this, because you have only one set of sensor, right? That means your output have only one bit. For one bit, it can represent only two situations. In this case, it stays still, doesn't move, and it's move or rotate, right? Only two conditions. But if you want to know more detail, for example, if you want to know that this plate rotate in clockwise or counterclockwise, that's more information, right? That means you need to add more bit, right, to represent more condition. Okay, so for example, in this case, I said 3 set of sensor. Each sensor give 1 bit output, and let me paint the array something like this, namely this transparent, okay, transparent, opaque or dark, okay, transparent, dark, and here transparent, okay, and so on. So if this area come to this sensor array, so what happened? So the output from this one become 0, right? 0 at here and 1 at here. Okay, it's dark. Okay, then the light, the reflecting light can go into the sensor. So when the light go into the sensor, so the sensor will give logic 1 output. If this plate turn or rotate in this direction, that means this area, right, will come to the sensor position. That means the output will change to 0 0 0, right? And when this area come to the sensor, so the output will be 1 1 1. Okay. Anyway, if this plate turn in counterclockwise, what happened? This area will go to the next one, so it become 0 1 0, and the next is 0 1 1. So it's different sequence of the output. That means now you can detect the direction of the rotating plate. Okay. And because of 3 bit, that means we can use this one to represent maybe 8 area on this plate. For example, if this area, okay, go to this sensor position, that means the output is 0, 0, 1, right? So you maybe know that, oh, this area, right, is over the sensor. But if your output is 0, 0, 0, that means this area, right? So maybe you may define this area like the degree, okay, to represent the disk position. Anyway, in practical, some problems occur. For example, if I paint the color for this area, but some color, okay, is over into this area or this area. What happened? What happened if this plate, okay, rotate in this direction? That means when this position, okay, go into the sensor line, what happened? The output will be what? 0, 0, 1, right? But it should be 0, 0, right? Okay, it is a little bit error occur. Anyway, this is error is acceptable because at the beginning it's 0, 0, 1, right? Then it's rotate, this move to here, then it's to be 0, 0, 1, okay? And after that it change to 0, 0, okay? Okay, that means it's acceptable. Anyway, what happened for rotate in this direction? If the color paint color over in this area, what happened? So when this area, okay, go to this sensor line, it will show the output of 0, 1, 1, right? However, 0, 1, 1 is not this area, right? Not this one and not this one, but this. So this is not so good, okay? So to solve this problem, you must observe, okay, why when this kind of error occur, and you misunderstand, right? Okay, to interpret which area now are in the sensor line. So it's quite, it jump to this area and jump back to this area. So it is not so good. That's because why this point is acceptable error? Because this area and this area are adjacent, right? Okay, but 0, 1, 1, okay, are not adjacent to this area. Okay, so it this error is not acceptable. But so why this one is okay but this one not okay? If you can observe this area and this area, the value that represent this area and the value that represent this area different only 1 bit, okay, only 1 bit difference. But this one and this one, for example, this one and this one, when it change from 0, 0, 1 to 0, 1, 0, it 2-bit change, right? 2-bit change. So for 2-bit change, if one of these change faster, for example, this area, right? So it become what? It become 0, 1, 1, right? 1-bit change. 1-bit change. Okay, before change to this one. But in this case, this area is in this, not be the next from this one. So let me rearrange the code for each area so that so that the adjacent area will have 1 bit difference. For example, this area 00, this area 001, 1 bit difference. This area and this area also 1 bit different at the middle. This area and this area, okay, is binary code and different only 1 bit. Okay, this one also different 1 bit. This one also, okay, have 1 bit difference. This one also 1 bit difference, and this pair also 1 bit difference, and this one. Okay, this kind of sequence is called binary. No. It's called gray code. Okay, gray code. Like this one. Sorry, this one, gray code. And for the at the original one, it's called binary code. Okay. Sequence is 00, 01, and 10, 11, 10, and so on, like binary counting order. But in gray code, okay, the next value will different only 1 bit. Okay, so now let's observe about the binary code and gray code, about its relationship. So for this one, that I use this right on this. For example, if I want to write down the binary code at first, binary code, okay, and this one may be gray code. For 1 bit, okay, 1 bit binary code. How can I write it? Maybe 0 and 1, right? For 1 bit. Gray code also 0, 1. Okay, 1 bit difference. Okay, and if I want to write 2 bit for binary code, what should I do? I just write down what? Beginning with 0, right? And the second half beginning with 1 and 0, 1 again, right? How about this? For gray code, if I start with 00, at the same as binary code, and 1, 1. How about this? Because it's 1 bit difference, right? For now, this bit and this bit only difference. Okay? Already, right? Already be different for this bit. That means this bit must be the same as this one, right? So it should be 1 at here. Okay, so it should be 1 at here, and then the next value, this value and this value also must be different 1 bit for gray code. That means because this one is 1 the same, right? This position must be the same, must be different. Then it must be 0 for this position. So be 0 right here. Okay, this is pair from 2-bit binary code to 2-bit gray code. And now if we want to write down 3-bit, okay, at binary first. For binary, if we want to write down 3-bit, again I add 0, 0, 0, 0, right? And 1, 1, 1, 1. And for this same sequence, right? Of 0, 0, 0, 1, 1, 0, and 1, 1. How about this? If I want to write gray code in 3-bit, again I start with 0 and 1, 1, 1, 1. So now, if I want this value and this value different 1 bit, so what should I do? Because this position already different, right? That means this 2-bit must be the same as this one. Okay, so it should be 1 at here and 0 at here. So it's 1 at here, 1 at here, and 0 at here. Okay, this part must be the same, right? Anyway, this bit is same, right? But this value and this value but must be different. Okay, only 1 bit. And because this one and this one different 1 bit, that means I can copy this, right, and write down to here. Okay, then I copy this one, write down here. Okay, and similarly, because this value different to this value only 1 bit, so I just copy this to this 0 1, and again copy this to this. Then I can obtain 3-bit gray code. Note, okay, 1 bit difference, right? 1 bit difference, 1 bit difference, and this one, right? Different only 1 bit at here, 1 bit at here, and 1 bit at here, and form it to this. Okay, 1 bit at here. So again, if I want to generate 4-bit gray code, what should I do? I just add, right? 0 0 0 0 0 0 0 and 1 1 1 1 1 1 1, right? And then copy, right, in this direction, right? 1 0 0, right? Just copy, and 1 0 1 1 1 1, and so on. Okay, now you know the method how to write down gray code and binary code. Okay, from 1 bit, 2 bit, 3 bit, and so on. Anyway, okay, if I know the binary code and I would like to calculate or convert to gray code that corresponding to this binary code, what should I do? Of course, you can do by starting with writing 1 bit binary code, gray code, 2 bit or 3 bit, and compare, right? If you write out like a table, you just find out the same row, right? This row binary code and the same row for gray code. So you can find out the gray code of this binary code by this method. Anyway, what happened if I want to find out binary and the gray code of this binary code? This one is binary code. What happened if the binary code is 0 1 1 0 1 1 1 0 1 1 1? Oh, it's quite wrong, right? If you want to know gray code, what should you do? If you write out the table, something like this, it take time, right? Anyway, you can do something like this. Okay, that you observe by yourself. At first, by this binary generation and gray code generation, you can observe that the MSB for binary code and gray code are the same, right? Okay, because you beginning with the first half with 0 and the second half with 1, right? So MSB bit of binary code and gray code are the same, and number of bits also the same, right? Then based on this one, if I want to find out gray code, okay, of this binary code, can you? Yes, you can. Okay, at first, okay, let you try to do it by yourself. Let me write this one. Okay, for this position, this one is 0. This one is what? 0 1 1 0 1 1 0 0 1 1 1 and 0. Okay, can you observe something? Can you do it? Okay, yes, you can, right? Actually, I just observe this one. Just compare this. If this digit and this digit are the same number, so the result is 0. 1 1 the same, then 0. 0 1 different, the result is 1. 1 0 different, this bit is 1. 1 1 the same, so is 0. 0 1 different is 1, right? Different 1, same 0, same is 0, different is 1, different is 1, different is 1, right? The 0, actually you can imagine that at the beginning, okay, this may be 0 at here, right? Or because MSB must be the same also. Okay, one more example. Could you write down code, okay, for this binary code? For example, if binary code is 1100101111011001. 01. Okay, again, this one is 1, right? Different, okay, different, same, different, different, same. This same, this different, 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 same. Okay, so difference 1, right? And same, and this bit must be the same. Okay, or you may imagine that there are 0 right here, right? When you compare this and this, so it's different. Okay, so and how about if I have gray code first, and can you find the binary code? For example, if this one is gray code, this one binary code, binary. If gray code is 1110001101, for example. So to find out binary code, okay, you can start from MSB. MSB might be the same, right? Okay, and you know that the gray code is 1, this bit is 1, that means this bit and this bit must be different, right? So this position must be different, so this bit is 1, so when it's different, then it must be 0 at here. Okay, and how about this one? 1, okay, must be different, right? This 1 and this is 0, right? Then it must be 1 at here. Okay, so 1 at here. Okay, 1 at here, and this bit is 0, right? That means this position and this position must be the same. That means it's 1 at here, it must be 1 at here also. So it's 1 at here. 0, this one, that means this bit is the same, right? The same. 1 means it's different, so 1 at here, different, then it's 0 at here, different, so it's 1 at here, same, and different. Okay, that's all. So now you can write the binary, okay, of this gray code. Very easy. Okay, so let's back to the PowerPoint. Okay, now you know the method, okay, to write down gray code and binary code. Okay, so you can do something like this. Okay, you can generate it. So for the circuit, for example, because you know how to generate, okay, binary code and gray code. Okay, that means if I have some binary code, for example, B3, B2, B1, B0 is binary code. If we want to convert to gray code, what should I do? I mean, I would be G3, G2, G1, and G0. I compare, right? This bit and this bit, right? That means I use what? Use XOR gate, right? If this bit and this bit different, output is 1, is the same, output is 0. So it's XOR function, right? This one XOR together. The result is G0. And then you will compare, right? Compare this bit and this bit, right? By using, again, XOR gate. Then you get this bit G1. And for this one, compare again B3 and B2, right? XOR together. And for B3 and GT are the same. Okay. So now you can convert 3-bit to 3-bit binary code to 3-bit gray. 4-bit binary code to 4-bit gray code by using 3 input XOR gate. Just for example. Okay. Okay. The next is BCD. BCD is from binary code decimal. Okay. The main word is decimal, right? Okay. For decimal, each digit of decimal number already contains and can have only 0 to 9, right? 10 number that can be in digit. Okay, so this position also 0 to 9, right? 0 to 9, right? Okay, for this BCD number system, we will write it down binary code for each digit. Namely, for example, 2, 3, 5. For example, I can represent 5 with what? Because 0 to 9, right? It need 4 bit, right? To represent, namely 0000 until 1001, right? That means 5. You can write it that 0101 for 5, and this position, right? 3. You can write with 0011, and this 2 is 0010. So it's very convenient, right? Because you just convert, right, digit by digit. Okay, change one digit in decimal to 4 bit in binary form. Okay, anyway, keep in mind that this 4 bit is 1 digit in decimal, so by itself is decimal. Okay, just change the number, the appearance from 0 to 9, okay, to 002 1001. So it is very convenient, right, to convert. It's faster than you convert to the binary code. Okay, for binary code you just divide it by 2, okay, again and again. But for this one, you just can remember 0 to 9. What is it? Binary code 4 bit binary code to represent 0 to 9. That's all. Okay, you can write down this number system easily. Okay. And for example, this one. For this, if I want to write down 2548 in BCD to I want to write down in BCD. So actually I can start to any digit. That means this 2 is 0010, 5 is 0101, 4 is 0100, and 8 is 1000. Okay, that's all. So in BCD you can write it as this one: 0010, 0101, 00 and 1000. That's all. This is BCD. Okay, 4 bit. Okay, 4 bit to represent each digit in decimal. Okay, now let's consider if we want to do some addition. Okay, let's add this one. 1 is 1, right? 0 is 0, right? 1 add 1 is 0, and carry out this 1, right? And then we add this one is 0, and I keep this 4 bit. Okay, so your result is what? Oh, sorry, this is 1. Okay, it's 1. Okay, this 1001, right, as the result. This is okay. Yeah, because this represents 4 and 5 here, right? And this is 9. Okay, so it's correct. Okay, no problem. How about this one? From this one, 1 add 1 is 0, right? Carry out is 1. 0 1 is 0, right? Carry out is 1. 1 1 and 3 in 1, so it's 1 is here and 1 is here. Is it correct? No, it's not okay, right? Because what? Because in BCD is position in decimal, okay? It can be 0 to 9, right? That means for 4-bit binary code to represent 0 to 9, the maximum is 1001. But this one is not okay. Okay, so what should you do? Okay, now the problem is you use binary code. You use 4-bit binary code. For 4-bit of binary code, normally it can represent 000 to 1111, right? But now you just use only 000 to 1001, right? You use 0 to 9, right? But itself for 4-bit is 0 to 15, okay? The difference is 6, right? That means if you do BCD addition and your result is greater than 9, what should you do? You should add more 6, right? You should add more 6, okay? To make this digit, okay, become the normal decimal value. Namely, if you add 6, so what happened? 6 is what? 0, 1, 1, 0, right? When you add to this one, so your result should be, previously the result is what? 0, right? 0 at here, right? 1, 1, right? When I add 6, okay, add 6 is 0, 1, 1, 0. So the result is 0, 1, and what is 0 at here, right? And carry in is 1, so it's 0 at here, and carry out is 1. So for this 4-bit, it's 0010. And about this, okay, then this carry out, okay, become the next digit. So it will write to 4-bit, something like this. So the result is what? In BCD, this is 1, this is 2. So it's 10, 2 is 12. Okay, how about the result? This one is what? 5, this one 7, right? When you do the addition, oh, the result is 12. It's okay. So for this BCD, when you do the addition, you must be check that the result is over than 9 or not. If it's become over than 9, you should add 6, okay, to do some adjustment. Okay. Okay, for the next example, also I do more one for this. 1 at 1 is 0, right? And carry out is 1, and 1 and carry in, so it's 0. It's 1, right? 0 is 1, right? So it's 0 and 1, right? Your result is what? 1, 0, 0. Is it okay? No, it's not okay. Even it is see that it's 0, 0, 0, 0. But carry out is 1. Carry is 1, that means your result is over than 15, right? If it's over than 15, that means it's over than 9 also. So you should add more what? Add more 6 to the result. So it become, and this one, okay? So I write this 4-bit and this 4-bit. So is what is 1 and 6, right? In. Okay, let's consider the original value is 7, right? And now, so it is 16. Okay. Okay, for the next page, that shows some other binary code for BCD. Sometimes it is called the weight is 8, 4 to 1. That means this bit have weight of 8, this bit have 8 of 4, this bit 8 of 2, and this bit weight of 1. For example, if your binary code is this, so this portion is 1, right? Weight is 4, this portion is 1, weight is 1, so you do addition between 4 and 1, then it becomes 5. Anyway, for this number system, this code is 2, 4 to 1. 2, 4 to 1. That means, for example, this bit is 2, this bit is 2, this bit is 1. So 1 0 1 1 for this system is 5. Okay. How about XS3? Okay, for the code for XS3, something like this. We use 0 0 1 1 to represent 0, 0 1 0 0 to represent value of 1, 0 1 0 1 to represent 2. Note the code for this system is XS3. Okay, when compared to the normal one, okay, when you add 3, then it's become this binary code. Okay, that means the code by itself, okay, but the value that it represents, okay, is XS3, okay, more than 3 as a normal binary code. However, this one is binary. For binary, for the lower value 0 to 0 1 2 3 4, it beginning with 0 1, okay, and the second half it beginning with 1 0, okay, and the 5 bit is to represent the value, right? 1 1 1 1 1, okay, to show the first value of this part, okay, the first value of this part, okay, and the second value of this part, third, fourth, and fifth value of this part, okay, which represent 0 1 2 3 and 4, okay, and this one also, right? For the second part, the first value of this part, second, third, and so on, okay, to represent 5 to 9, okay, that's all. And the next number system is 1 out of 10. For 1 out of 10, there are 10 bits, and every 1 bit is 1. Like you have 10 fingers, right? And each finger to represent the value from 0, 1, 2, until 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? If you want to show the value of 1, so you set let this bit, okay, become 1. To show that, oh, its value is 0. This bit become active. And if the bit active, that means now the value is 1, okay, and so on. The system is called 1 out of 10, okay? 1 out of 10, there are 10 bits. Only 1 bit have a value of 1. And one more thing that you should note is, for example, for BCD, you use 4 bit, right? But 4 bit by itself, it can represent up to 15, right? But you use just from 000 to 1001, from 0 to 9, right? But for 10 to 15, you don't use, okay? So this is unused, okay, code word or non-code word. For XS3 and 2 4 to 1 also. For binary, okay, also have unused code word. 1 of 10 also, a lot of unused code word. Okay. Now let's consider if I want to, for example, to send some data in digital code, okay, in binary form. This one may be transmitter. You want to transmit the data, something like this, okay. And the receiver. This one is the receiver to receive the data. Okay. Of course, it is possible that some noise, okay, disturb and make the value change. For example, it may change for this bit, okay, then it may be 1 1 0. When it change, it may be 0 at here and 1 at here. So some error occur, right? Okay, if it change only one bit, it's called single, okay, single bit change or single error. Okay, so also 2-bit also possible. Okay, 3-bit error also possible. Anyway, if based on independent error model, and the most or the highest possibility that can be occur, okay, just is just only single bit, okay, or single error. So for this class, okay, we just consider in the case of single error. Okay, for 2 or more, if someone who interested, you can study more deeper in maybe 3 or 4, okay, in communication. There's some subject about coding. Okay, by the way, okay, let's consider in the case that the error occur only 1 bit. So let's consider this one for 3-bit code. If I use, for example, 111 to represent A, 011 represent B, 110 represent C, and this one is 4D. Okay, like answer for multiple choice problem. If I want to send this code to represent A, 111, okay, send, and if some noise occur, so what happened? If 1 bit error, if this bit error, so the receiver you see 110, right? This bit error. So the receiver 110, maybe the receiver maybe understand is it what? It's C, right? Maybe understand that the transmitter send C, okay, to the receiver. So if 1 bit ping at the middle, that means go to 101. So what happened? The receiver maybe understand is D, right? Okay. Now if again this one is A, B, C, D, right? If the transmitter send the letter C, okay, send the letter C, if 1 bit ping, 1 bit error occur, for example, if this bit ping, so it become 1, 1, and 1, right? So the receiver maybe understand that the sender send the 1, 1, send the letter A, right, to him, right? But what happened if the error bit is the first one? That means the receiver will see what? 010, right? Okay, for 010 is this one, right? Okay, if there is no meaning, that means the receiver will know that there is some error occur, right, during the data, okay, transmit to some media. So the receiver maybe request the transmitter to send the data again. Okay, what difference between this situation and this situation? This situation, when some error occur, the receiver don't know, because the received data have the meaning. But for this one, when the receiver get the data, but this data have no meaning. So there's some error occur, right? That means if I want the system can detect that some error occur, we must design the system so that if one bit change, okay, if the one bit change or one bit error occur, the new code must have know the meaning, right? Must have know the meaning. That means, for example, for this one, okay, this dark dot have the meaning, this dark dot have the meaning, this dark dot have the meaning, this one have the meaning, but this the light, okay, light color, light blue have no meaning. It's non-code word. So for this one, again, it represents letter C. If the error occur at this bit, that means it's changed to this one, no meaning. The receiver no. Some error occur, then request the transmitter send data again. However, if this bit is changed, that means it's changed to 0, right? Then it becomes 1 0 0, okay, at the receiver. Now the receiver get this code. Oh, no meaning again. That means some error occur. Then request the transmitter send data again. How about this? If this bit error, so it become what? 1 here, right? So when the receiver get 111, oh, no meaning. It's non-code word again. So let the transmitter send data again. Okay, something like this. Oh, okay. This is the basic, okay, method. That mean if note that if this one is code word, note there are two, right? Two ones, okay. With if one bit change, that mean we change maybe have only one or three one. Namely, if this code word have even number of logic 1, when it change one bit, again non-code word must be even, right? No, must be odd. Okay, odd number of logic 1. Okay, again, if you define the code word with even number of logic 1, that means if one bit error occur, so the result will be even, right? No, not even, sorry. You change from even to odd, right? Even number of logic 1 to odd number of logic 1. That means if your system, the transmitter and receiver, okay, do some agreement that for the system, okay, you have only even number of digit 1 to represent something. That means if the receiver receive odd number of digit 1, that means some error occur. Okay, so if I have some information bit like this, if I use 3 bit to represent 8 things, if I send this data directly, what happened? If 1 bit error occur, so the receiver cannot know, right? Because if 1 bit, for example, if this bit, he will send this one, right? If this bit become error, so the receiver will get 111, right? And 111 have the meaning. So what should we do? So you should add, right, more 1 bit to check that all of this, okay, is maybe even or odd number of logic 1. So you should add more 1 bit, and this bit is called checking bit or parity bit. For example, if you use even parity code, that means you must add this bit so that the total number of logic 1 is even. For example, if your original information is 001, right? Okay, if you use this event parity code, that means you should add what? Add one at here to make total number of 1 become even. Okay, if your original information bit is this one, 0, 1, 1, so you must add 0 at here, right? So that the total number of logic 1 is 1, 2, okay, it's even. By the way, if you use odd parity, okay, so the parity bit, when you add it, the total number of logic 1 must be odd. Okay, that's all. So let's consider this one. What happened if I again for this, if I send this one, okay, and send, and if the receiver get 1, 1, 1, okay, get from this one, if the receiver know that this bit is the error bit, that means the receiver, okay, can do some correcting by itself, right? That means if this bit error, that means the correct one must be 0, right? Okay, so that means the receiver need not to request the transmitter to send the data again, right? If the receiver know, right, know what the position of the bit, that become error. Okay. Anyway, but for this system, if you add just only one parity bit, if the receiver get this one, if we use this even, if you get 1 to the odd, right, odd number of 1, so it may be either from this information bit, or it may be from this one, okay, or from this one, right? There are 3 possible ways, so the receiver cannot make the decision that which bit is error. So the receiver in this case cannot, okay, do some correcting by itself. So the receiver need to send the request to the transmitter, okay, to send data again. So if for example, if I have 4 bit, 4 information bit, 4 information bit, if I add 1 parity bit to check, that means now I just can check that there's some error or not, right? But if I want to know the position, which bit is error, that means I must add more checking bit, right? So the question is it enough if we add 2 bit to check? Is it enough? Maybe not, right? Because 2 bit can represent 4 situations, right? Okay, 4 situations. Okay, maybe this bit error, this bit error, this bit error, this bit error. Oh, it's 4 situations. No. Because the second bit itself also possible to be error, right? That means it cannot cover in this case. Okay, so if I add more one bit, totally 3 bit to do checking some error, and I want to know the position for 3 bit, it can represent 8 situation, right? Namely, for single bit error, this bit, 1, 2, 3, 4, right? Or this bit, and this bit, 7, right? Okay, 7 case of single error, and no any error. Okay, no any error. So 8 situation. So that enough, right? Okay, that enough. Okay, let's show some of this. This 3, right? Sorry, 4 bit, and add 3 check bit or parity bit. If you do this one, you can check the position of single bit error. Okay, how does it work? Okay, let's consider this one. Okay, for information bit, there are 4 bit, right? Maybe this 4 bit. Okay, and I will add more 3 bit, Okay, let I group this like this. For G1, group 1, group 1 contain B1, B3, B5, and B7. For group 2, G2, there are B2, B3, B6, and B7. And G4, okay? B4, B5, B6, B7, okay, are in G4. Okay, now, if your information bit, this 0, 0, something like this, okay? If I use event, okay, event parity for group G1, I must add this one so that total number of digit one is even. So I must add 0 right here, right? Okay, so right here. And for group G2 also, I want to make even number of 1. So 0, 0 right here is must be 1 right here, right? Okay, for G4 also, if we want to make even of 1, so it should be 1 here. Okay, that means so now the value of this is 1, 1, 0, 0, 0, 1, 1. Okay, or when you send the data, it's maybe something like this. Oh, sorry. Maybe something like this. B1 is 0. What happened? B1 is 0. B2 is 1. B3 is 1. B4 is 1. B5 1. B6 B7 is 0, 0. Okay, send the data. And for the receiver will check that in group G1 number of 1 is even or not, G2 also, and G4 also, if all of these 3 groups, okay, contain only even number of 1, so it may be concluded that the error may be not occur. But if some group, okay, is odd number of 1, that means some error occur. And if it's a single bit error, so the receiver can check, can know that which bit is the error bit, and then can correct it by itself. For example, if this bit error, okay, that means the receiver maybe get 0, right? Get 0. So before at here, right? Get 0 at here. So what happened? This group, okay, let's consider this group, the 0 will get this one, right? Okay, it's even. Okay, it's okay. Number of 1 is even. Okay. How about this? Oh, it's odd, right? Not even. So it's odd early group G4. So we can conclude that the error bit is B4. Okay. Another example. If the error bit is what? B6, for example. If this bit become error, that means it become 1 at here, right? It's B6 become 1 at here. So what happened? what happened when you check, when the receiver check this one, okay, it's even, right? It's okay. This one, oh, it's odd, right? 3 of 1, right? And how about this? Oh, this one also odd, right? 3 of 1s. So this group error, this group error. So you can conclude that it's what? 2, 4. So it's 6, right? Basic error. Okay. So you can know that the error position is basic. That means you can change, right? Change the value by the receiver itself. That means this position, this one, okay, change to 0. So the receiver can correct by itself. One more example, if the error bit is from B7, so what happened? This one at here, this is one at here, and this is 0, right? Okay, error bit is occur at B7, so this group is not even, right? It's odd. This group also odd, right? 1 1 1, okay, and this group also 1 1 1, okay. If all group incorrect, okay, mistake, some error, okay, so you can conclude that the error bit is B7, okay. For this technique, okay, it's actually it's called Hamming code. And I try to show you some this Hamming code. It is called minimum distance 3, okay, for this one, namely for the code word, this code word and this code word with different 3-bit different, namely this bit, okay, 1 bit different, this bit also different, and this one, okay, 3-bit different is called distance 3. Okay, what happened if, okay, if for example, when you send data of this, if 1 bit error occur, then become this, the system can do correct by itself. That means we change this 1 to 0 by itself. Okay, for 1 bit error, any position it can change back to the correct value by itself. But if 2-bit change, maybe, or 2-bit error, for this system cannot support. Okay, for example, if it change 2-bit, for example, if this bit, and maybe what else? Did bit change? So it's become 1 at here and 0 at here. So let's go to somewhere 1 0. Okay, we go to some root that the system cannot know, right? So it cannot convert back to the correct one. Or if you change 2-bit, this bit change, okay, to here. If only 1 bit change, okay, it can correct, okay, back to the correct answer by itself. But if it change more 1 bit, first of all this bit, so it changed to here, right? The system maybe understand that it maybe understand, or maybe this bit change, then it's maybe correct to this one, but it's not true, it's not correct. So this system can support only 1 bit, okay, 1 bit error that can do the correction by itself. By the way, for minimal distance 4, okay, for distance 4, like this code word and this code word have 4-bit difference. For this system, if 1 or 2nd bit error occur, the system can do the correction by itself. But for 2-bit error, okay, we change to here, the system can detect that some error occur, but cannot detect which are the error bits. So the receiver must send the request to the transmitter to send it again. Okay. Okay. For the detail, actually, for this system, if the code have the different in with 2C plus D plus 1 bit, okay, it can detect error, okay, no more than C plus D bit, okay. And if some error, okay, less than or not more than C bit, so it's possible to correct, okay, the error by itself. Okay, just some conclusion. Okay, that's all for this chapter.